Thank you. My name is Obi Anamnachi. I'm a contractor with an Ankh Corporation who I've been working with since about February this year. Um, Today, we're having, for now, the last part of my series on machine learning with Spark and Cassandra, which is on model deployment. This series has been going on a little while. But previously, we've talked about environment setup, how we set up the environment with Spark and Cassandra that we're using now. It's built on Datasets Enterprise. We've talked about data pre-processing, going through a couple of various data sets to see what types of pre-processing need to be done to get them ready to use with various algorithms. We've gone over testing, which is about the actual like mathematical, statistical like operations that you would use to test a machine learning model. Cross-validation is about the process of actually testing a machine learning model in process um, and getting out statistics that measure its performance. Model selection test is about different types of tests that can tell whether or not one model is better than another on your various data sets. And today we're talking about deployment. Um, it's been mentioned before, but if you have any questions during this, um, you can put them in the chat and we'll get to them in between sections or at the very end. The way that today's webinar is going to be structured, we're going to go through an introduction where we talk generally about model deployment, what some of the requirements may be, and where it falls in your general machine learning process. And then we'll go through some of the specific things that you have to consider when deploying a model and your different options there and how they might affect what you can or cannot do with that model. First question, obviously, what is deployment? So deployment, it's a process of multiple steps. We do it when we have a model. It generally involves moving our trained machine learning model somewhere from where it's sitting. So a lot of the time we have an environment specifically set up for that. In this case, it involves Spark, Cassandra, Jupyter notebooks, etc. And we need to move it somewhere that we can present it new data and have it do the processing and have it return results without tying up all of its resources doing that. Um, Generally, you want your model to be a part of a wider architecture, either storing the results for later use elsewhere or giving them back to a user. Um, and the architecture that handles that can be as big or as small as is necessary. And there are lots of choices that need to be made about the different parts of that architecture to facilitate what you actually want to do with your model. In this case, the data management of getting new data to your model, getting results to your user or to wherever it is that they're going to be stored or made use of. Um, Handling incoming requests. So when someone decides that they want to use your model or you decide for them that they're going to use your model, like in the case of e-commerce recommenders, just by using your site that you are deciding for them that their preferences will be subject to machine learning in order to give them recommendations. Um, and then the last thing on this list is whether your model needs constant replacing or retraining or occasional replacing or retraining, or if you're just going to continue using it no matter how badly the performance deteriorates. So we deploy our models in the last step of the process. We've used this graphic before. You can see over on the right, the last section labeled prediction is where moving your model into production or deployment happens. So everything we've discussed previously comes before this. And before you ever get here, your model should meet some performance threshold that you decided on previously. And all of your data pre-processing has to be solid. You can't make any changes to that process because data that's being sent in to be processed by the model in production also needs to have all the data pre-processing done on it, depending on what you allow to be sent to your model in the first place. All right, so the first step of our deployment process is transferring the model to where we want it to use it. So we're moving the model itself, which is some amount of data that varies depending on what model you're using. For example, like a random forest classifier is bigger than a single decision tree classifier because it's made up of several of them. And smaller neural networks take up less space than bigger neural networks. So even depending on how big your model gets, even that transfer itself can be something that you have to plan for. You want to move it into a production environment, but there's not necessarily anything we can say about that production environment except that it has the resources to do processing at all. Um, Specific methods for transferring models work for specific models. Um, some of these methods are cross-language. You can take a model trained in Python and it will work in R or in Java or some other language. Over on the right, you can see there's an example of an O in X representation, which we'll talk about in a little bit. But essentially, it's all of the processing steps that your model is doing, but generalized so that it is basically language agnostic. Anything that can understand this sort of, it's presented as a chart here, but it's actually more similar to a text file in practice. Any system that can parse it and do those computations can indeed load your model. So the formats that we're going to be talking about today are first, Pickle is a utility that can save basically any Python object to a file as long as you are willing to potentially write functions for that. So a lot of Python modules have the necessary functions already built in to basically all of the classes that you're going to be using, but not all of them, especially um, so PySpark has its own saving and loading utilities as of, I think, Spark 2 point something. It originally did not have it, but it was added to Apache Spark, and thus the changes have filtered through at PySpark. Um, but those will save your model to a different format, which is not necessarily the same as Pickle. The good thing about Pickle is that any Python environment essentially will have access to it. Um, so depending on your classes, um, the ability to move things between Python environments specifically might be all you need. ONNX is another format. It's meant specifically for deep learning models. It's something neural networks. Um, I forget the actual acronym, but essentially it's meant for neural networks. But it does support some specific other models via the like processes that it can actually describe. Um, it has inbuilt support for some machine learning libraries, but not for all of PySpark. Some PySpark models are indeed supported, but not all of them. And PMML is a predictive model markup language. Specifically, it's for predictive models, so it wouldn't do things like reinforcement learning. Um, It supports a small number of PySpark models as well, but again, not all of them. And the main thing about PMML is that it's very old, and thus it's compatible with a number of other tools, but potentially not with more modern advancements. So if you have a like cutting edge AI model coming out from Stanford or something, um, you won't necessarily know whether PMML will be able to handle this. Um, but it comes with a bunch of other tools that might make using PMML your first choice. Um, like I said, there are other model formats. PySpark, which we're going to be looking at later, has its own. That's not any of these. But the main thing is to be able to save your model to a file or a database or somewhere, and then get it somewhere else. Next topic that we're talking about is service architectures. Service architectures handle how your model gets new data and where the results go. Um, what you need out of a service architecture is enough processing power at the actual processing node to make predictions, a system that handles requests and results, and an architecture that will manage those resources, the computing power for the predictions, the requests, and the results. Um, Generally, you do not want any step of your process to hog all the resources or or block new requests coming in or new results going out. And one of the ways you can see this is over on the right, there is sort of a generalized front end. Um, this is from one of the articles that I used to write this webinar. But essentially, it has a Keras model behind it, and when requests come in, they get put into a queue. Workers process them one by one, so that when requests come in, even if you are still processing, you can still put those in the queue. Something you don't want is your entire system to be held up doing processing, such that if new requests come in or old requests have just finished and the results are sitting around, the people who want those things won't be able to get them. Something you want to avoid. So a couple of architectures, or I guess generalized categories of architectures, are distributed web services, where the resources are split up based on tasks. So the one I described earlier, where you have an internal job queue, a front end that takes requests and directs into that job queue, workers who take requests from the front of the queue and process them and send them back to users. That's an example of distributed web service because each of these services has their own jobs and they don't need to be on the same machine. In-app processing is a little bit similar to distributed web services, except that whatever is handling the back end or the front end even, if you use something like TensorFlow for JavaScript, um, is also doing the processing. So you can fall into the pitfall I described earlier in this, where the processes of the app are all held up and thus no new incoming requests or outgoing results will be able to get through. And you also need a language that can handle both the model and running the app itself, like I mentioned with TensorFlow for JavaScript. Um, You can use database integration. Some databases have these advanced analytics capabilities that can be used to insert Python or R code directly, arbitrary code written in certain languages, or can load and work with PMML or ONNX or other model formats specifically. And you can also set everything up in a publish subscribe method with streaming data, um, where whatever is handling the processing of your model also handles streaming data in or out and can publish results to people who are subscribed to them. And then the next thing we need to discuss is processing styles. Generally, this is batch versus real-time processing. And depending on what the thing is that you're trying to use your model for, you will choose between them. So real-time processing predictions are made one at a time upon request. It's very important if you need to get your results immediately. For example, the e-commerce example mentioned earlier, where a user logs into the site, they need recommendations right then. And if you have not generated them previously based on their profile, if you need to generate them based on, say, the item that they're looking at that exact moment, then some real-time processing needs to be done. The load of a system that does real-time processing is entirely based on user requests. And so you can have spikes when a lot of users are using your system, or you can have a lot of resources just sitting there if no requests are coming in. And it generally requires closer monitoring because any problem there will stop any incoming people from getting any sort of new results. In batch processing, feature sets are stored and processed together. So you might have a table or database entirely full of incoming requests that have all their data together. Oh, and this is something I failed to mention earlier. as part of the architecture section, but sometimes when a user sends in a request, it does not come with all the data. For example, again, the e-commerce idea, the person who is looking at a web page, you have that information, what web page they're looking at in the request, but you don't necessarily have the entire rest of their customer profile. And having them send that to you, um, say, get it from your system and send it to you along with the rest of the request, can waste a bunch of your resources. So part of what you might need to do is have a process that takes incomplete requests and goes and gets data from other locations to fill them out. Um, and this is something that batch processing excels at, because all of that can be done in the time in between data coming in and processing starting. Um, Batch processing definitely requires more consistent and longer term storage than real time processing. And the load is based on your own choices of batch size and timing, how often you want to run all your requests through as a batch, and how many requests before it triggers automatically. Okay, so our last topic for right now is model retraining. Generally, when you're working with a machine learning model, you want to keep an eye on its performance, because over time, with changes in the data that's coming in, you could be seeing better or worse results than you might expect. So you keep an eye on it, and if your performance declines below a threshold, you need to update your model somehow. You can do it by hand, use the same processes we talked about in previous parts, um, to gather data, train an entire new model from scratch, and then transfer and replace. Or it can be part of your architecture that automatically sees new data coming in and potentially uses that to train an online model. Some models, even when they are in production, new data can be fed in, their performance can be changed based on that. Um, Some can be updated from a previously trained model. Like, you can grab a neural network and just do more back propagation steps if you wanted to, and continue training it from a point where it has already been trained. Or some models don't have that capability, and if you want a different model, you're going to have to start and retrain from scratch. Um, The processes that handle this kind of thing are many and varied. You can use AutoML frameworks to do this programmatically. You could do it by hand. You could set up a system yourself for doing it. All of these are valid. It depends on what resources you have available and what needs you need to fulfill. All right, so we're going to move on to a demo really quickly, but we'll stop for a minute or so to see if anyone has questions that can be answered now. There will be time for more questions after the demo, but right now, if you have questions, you can put them in the chat and I'll do my best to answer them. Okay, I do not see any questions. If you have them, but just have not finished typing them, they will all be handled after we finish with the demo, and any questions that come up in between now and then can also be handled then. So this is our environment. You can see a bunch of the previous notebooks from previous weeks here. All of them are available in a public GitHub repository here. We'll put that in the chat really quick if people wanted to follow along. This is not really something that can be run without preparation, because the underlying containers already have certain Python models, already have certain Python modules, installed that we will need to do a process. Although it is also possible to use pip from inside Python to install them yourself. As you can see, We have used a bunch of different PySpark um, features, as well as some other modules. The new ones for this week, and for this one doesn't actually use Pickle. Um, for this demo is the PySpark pipeline model. Um, it's not something that we used in the past, but what it does essentially is you can take a number of processing steps that are happening within a PySpark context, and you can turn them into a single object so that 3, 4, 5, however many steps are in your process, including the data pre-processing and the actual training of your model, can take place all at once. It also makes it easier for saving your completed model, because rather than saving and loading 3 or 4 different parts, you can do it all as one part. We have our helper functions, one for nice formatting of PySpark data frames. By the way, everything that we've done in this series so far has pretty much all used the data frame API for PySpark rather than the RDB-based API. We start off by connecting to our Cassandra cluster. The data set that we're working with today is something that we've done previously, is the Pima Indians diabetes database. So it takes in a number of different factors, and what it spits out is a prediction, diabetes or not diabetes. This one always takes a little while, but we're building our Spark session here. And then we're going to print out how many rows were in that table. Basically what this does is it starts a Spark context, and then Spark is used to read all of the data from the Cassandra table that we created into that Spark context, into a data frame for use later on. So this is something that we did in our data pre-processing webinar. But basically what we're doing is we're weeding out missing data. We replace it with a NaN value so that it's not confused with valid 0 values. And then we are taking those missing values and using PySpark's imputer class to insert values into those locations that are missing based on averages of the data that is there. So this is the first time we've seen model.save. Basically, the way this works is that model.save is actually just an alias for a function in a new class which was introduced called MLWriter, which handles the saving and loading of machine learning MLlib models. So we have a line here that drops rows that still are missing values after the imputation, but there actually are not any, so we keep our full 768 rows. We run it through the vector assembler to get a features column, which contains all the features necessary to run our model. We split our data into test and train, and then we fit a random forest classifier to it. Like I discussed earlier, a random forest classifier is made up of a number of trees, in this case 10, and this is a random forest classifier, so it randomly chooses between them, but that still gives better performance than just having a single decision tree. You can create something called the voting classifier, which is made up of a number of other classifiers that then vote on which response they want. And we look at the performance. And here is where we assemble our pipeline. So we did not actually have to do all that stuff with actually running the vector assembler and actually running the imputer, because what we're doing is we're taking all those classes that we made after they are trained but have not yet been used to transform the data, and we're pushing them all together into a pipeline. So we do that, and then this time we resplit our data because last time the thing that we split up here is the data set that had already been fully transformed by all of the intermediate steps, but not the predictive classifier. So instead, we're splitting here an old data frame that has not yet had all that processing done to it. And then we fit our pipeline based on all the incoming training data, and we use it to run predictions. So you can see we're getting our predictions out here, same as ever. And all of the rows that were created by the step-by-step process are also created by the pipeline. And what we can do here is we can save that model. So Jupyter Notebooks won't open the actual model because it's not readable. But we can look at the metadata and see that what we saved is a pipeline model with these parameters, et cetera, it's made of imputer, vector assembler, and a random forest classifier. And PySpark can use this data to then load your model back into Python, which can be seen here. And we can see that we're also getting predictions out over here. So this is not a full deployment pipeline, even a little bit. It's mostly the just saving and loading of a model. But I did not have time to write up a full architecture for this sort of thing because I was busy trying to figure out O, N, and X, which I did a little bit. Has any of this been run? Yes. Good. So as you can see, we can save our models the same way, except that O, N, and X models are pure hex strings. And one of the interesting possibilities that one of the interesting things that this makes possible is that rather than saving to a file and moving that file, we can then, I mean, we did it anyway here, it is possible. As you can see, we have models here. Again, not human readable, and so Jupyter Notebooks won't open it. But if you look at it, it's basically this. You have hex things, and then you also have some small text descriptions interspersed in them. And you actually can, have I done that anywhere? Here we go. If you have a loaded ONNX model, you can print it out and get it in human readable format to see how it actually stores things. For example, one of the earlier parts here is called a split node. And if you see what it's doing is it's doing the imputation, the same transformation that the imputer does, that takes in this case, it's BMI, plasma glucose, blood pressure, tricep thickness, and serum insulin, and it spits out those 5 rows plus, but with different data, with the missing values imputed. But like I was saying, one of the things that this makes possible is that you can actually create a Cassandra table and load your model into it. So as you can see, we've done that here, and then here we've selected from the Cassandra table to read that same model back out again. And that's actually an interesting an interesting capability to have because it opens up a lot of possibilities for your model retraining. You can be constantly training models and loading them in Cassandra, and then requests come in, you grab the most recent one from the Cassandra table, load it into memory and run. Um, and the reason that this did not leave me much time for putting together a full architecture is because I've had trouble working with PySpark and the ONNX runtime sessions. Um, I have not been able to figure out the problem. Uh, but if I do, you can expect an update to the GitHub repository here with working code. Um, but for now, that is the end of our demo. So we'll be moving on to questions. If you have questions, you can put them in the chat. There's one there already. Is it necessary to install Cassandra? Yes. For this code to work, you will need access to a Cassandra cluster and then also the Python Cassandra driver. Uh, it is not pip install Cassandra, but if you look up Python Cassandra driver, you can get a install command that will install it. Any other questions? All right. This has been Obi Anunashi with Anant Corporation. If you would like to talk more on this subject or any other subjects related to Cassandra, you can feel free to contact me via email. My email is not on this slide, but it's obioma.anunashi@anant.us. The blog post for this will come out tomorrow, probably. Um, and feel free to come to any of our future webinars. My next one will be on DataStax Enterprise Graph, just a very shallow introduction.